Hey, handsome. What? Girls can be handsome. Why am I lethargic? Because I hate my life. I just finished explaining to you for like 20 minutes what's going on, and the video was on pause. That's okay, it's only you. You got time, so just chill out and let me regain myself. I'd like to pick up where I left off yesterday, thinking about gravitational waves, okay? And I need you to just get through this, okay? I know you're not going to understand anything I'm saying, but it's important because I'm explaining it, okay? So, assuming you know absolutely nothing is where I'm forced to begin. The universe is whatever you think it is. Your conception of what the universe is exactly right. It is exactly what your universe is. The phenomenon is that your universe is able to think about itself and its place in its universe. And so long as you can do that, we are akin. And so allow me to explain to you my universe. On June 29th, 2023, the Astronomy Picture of the Day released a visualization of what the universe is in, what your universe is in. How you are able to think about the universe relies on you being coupled to something, right? You're coupled to something, and it's not the Earth, because the Earth is coupled to something, and it's not the Sun, because the Sun is coupled to something, and it's, and so then you realize, okay, it's space-time. Congrats. You can't travel through space without traveling through time, right? You want to come see me? Well, you're not here now, so you get it. Furthermore, Einstein himself was the one to theorize that it was the matter we know and love, baryonic matter, touchy-feely atoms matter, right? There's a lot of other matter out there, but we're only talking about matter that matters. So the matter that matters apparently deforms the space-time of the universe. Your universe. Right? So if you were to create a clock, and it was the most precise clock you could ever possibly imagine to create, it would be called an atomic clock. And what that atomic clock would do is it would measure the time it takes for an electron to jump instantaneously from one spot to another. So when an electron just goes doop doop, disappears, reappears, it emits a photon of light. And when that photon of light is emitted, it can be detected. And so if you had a photon or an electron that was naturally or artificially or reliably moving from one space-time to another space-time, it would consistently emit a photon of light, an electromagnetic photon, reliably. And you can confine it to a very small piece of space-time and synchronize your two clocks so that their signals were matched. And then you take one of those clocks on a journey, and it doesn't matter how far and it doesn't matter how fast. What matters is your ability to detect the change of timing. And so after you took one of these atomic clocks on a voyage around the Earth and returned it to the proximal space-time that the other one was in, you would notice that the one that had moved has been delayed. Okay? A travel through space-time will delay everything compared to the clock that didn't move. Okay, everything's moving through space-time, and one moved through space-time more, and when you bring one that has moved further through space-time back to the one that hasn't, there'll be a mismatch, and the one that moved will be going slower, noticeably, if you've gone fast enough or far enough. Okay, that's how you measure space-time distortion. Okay, why that matters is there's a thing called triangulation. Okay, and again, this is a long slog, man. So just bear with me when we talk about triangulation, okay? So if you knew that a lighthouse was sending you a signal every second or whatever, and there was another lighthouse sending you another signal, and if your timing was precise enough, and if you were on the same plane, you would be able to know how far you were or where you were with regard to those two lighthouses, right? So if you're on the ocean, a single plane, and there's 2 point sources pinging at the same time, as you travel through that field, you would know where you were. And let me see if I can find... Okay, you know what? I don't care how quality is, right? So imagine yourself on this ocean traveling around, right? It doesn't matter that it's a static image. You can imagine those pulses, waving towards you. But as you would move around this field, you would know where you were, at least with regard to these 2 point sources on a plane. Okay? If this was extrapolated to a 3D thing, you could only know where you were in a single circle. Okay? So if you have 2 points, you get to know the circle that you're between them, right? And so if you're on an ocean, your 2 points are here. But if you're in a 3D space, your 2 points are any circle that would account for the time delay in the signals, okay? If you were to add a third source of information, you would then know where you were on that circle. Add a fourth, you get more precision, etc., etc. That's exactly how GPS works, okay? So your GPS, when it's trying to find your spot on the Earth, is looking at the timing signals of these satellites that are going around us, and we know where they're supposed to be, and we know how long it takes for their signal to get to your clock, and then your clock knows where it is on the planet, inside the sphere created by the emission signals of the GPS satellites, okay? Okay. Okay, but wait, you say. Didn't you mention that things that are moving, their clocks get mixed up compared to the things that aren't moving? Right? I'm here down on Earth, but these satellites are moving around in space. They're going a lot faster. How can their clocks keep the same time as me back down on Earth? Well, it turns out that we need to adjust for how space-time is distorted in this scenario. So we need to, and that is the outcome. Programming GPS satellites to account for the space-time properties that we all exist in is proof that Einstein was correct when trying to solve the problem of the transition of Mercury. Huh? What? Mercury? What? No, guy. Not Mercury. Come on, we're talking space-time, brother. General relativity Mercury. So what happened is, when we thought we figured out that the planets orbit in a particular ellipse that is based on the radius and the masses and all this stuff, we thought we had it pinned, but then we started looking at Mercury. And because Mercury is moving so fast around the sun, and the sun is so huge, that it wasn't where it was supposed to be based on our earthbound or earth-based calculations. So it took an incredible mind to come up with the idea that the matter itself, the baryonic matter itself, was distorting the space-time around it. And as a result, a new math was invented, and general relativity was born, and 100 years later, we can make GPS satellites based on the fact that we know why time gets all screwed up the minute you start moving around. Okay? Okay. So. Yeah, but man, you said we knew about at least having the idea about gravitational waves and general relativity 100 years ago, and we knew that we had to reprogram our GPS satellites 10 years ago. What are you telling me about this discovery? Right? What is it that we need to know? Like, didn't we already know that big things moving fast perturb the space-time fabric? Right? We know this. But now they've confirmed that there's this background. And again, I don't know if it was in the previous recording or this recording, so maybe I have to listen to this again, but monitoring 68 pulsars. And Jesus, man, now we need to talk about pulsars. What are pulsars? Okay. Pulsars are the atomic clocks, okay? They are beacons, the lighthouses, out in the universe, infinitely far away. And they've been shining a light our way ever since, okay? So some stars out there have failed in such a way that they have a beam of light. Well, I guess, you know what? I'll just click on pulsar. Let's see what pulsar brings us. Ta-da! Ah, perfect. So, this is a representation of an emission from a rotating celestial body, okay? And these orbiting, spinning masses can spin reliably enough that we can set our clocks to it, okay? So once you get a star spinning, there's not really much that can stop it spinning reliably. It's all out on its own. It's just spinning around. It's huge, right? Like, even if another little planet comes in, it doesn't really bother it. This is a static source of a constant signal. And we've been monitoring these signals. And we know that anybody that's able to measure at least 3 of these signals will know where they are in relation to the rest. Okay? I know. I know. Deep end. Okay? Just stick with me. Most likely before you were born, this little doozy set off to see the universe. Okay? It's called the Voyager program. On board, thanks to Dr. Carl Sagan, was this golden disc. Okay? And it talks about some of the fundamental properties of the universe in which we live, right? So here is, I don't know, hydrogen. Here's like a hydrogen tube. But the most important thing to notice on the bottom left of the graphic is like that starburst. What that starburst indicates is our position relative to a number of known pulsars and the timing intervals associated with each, right? So because we have these beacons, these lighthouses, these rapidly spinning pulsar stars, we can show the aliens where to find us. Because if you go this far from this one and this far from this one, that's where we'll be. Okay? Brilliant. So finally, we can talk about a major discovery of loud gravitational vibrations across the entire universe. Anton Petrov is smart, and as like that's it. He's smart, and so what he's saying is because of the time differences that we've monitored from those pulsars, indeed, the fabric of space-time vibrates across the entire universe, okay? And so what I'm basically trying to say is, duh! Because, again, I have no idea what cut this is. I said, duh, because we've known for a very long time that gravitational waves perturb space-time. We had to reprogram satellites, and later on we made an experiment, right? And this experiment was designed to catch those gravitational waves, okay? So instead of measuring lighthouses out in the universe, we built an experiment to check here on Earth whether the planet itself was contracting or expanding as a result of what could only be speculated to be gravitational waves, right? If our theories of gravity are anywhere close to correct, the Earth should shrink and expand as the waves bob us up and down, okay? The problem is the size, okay? You need you're talking about what could arguably be a very still lake, okay? When you reach for your cup or your bar, you're not worried that it's going to shift away in any meaningful amount. But as you are reaching for your object, it is, it's moving, right? Either it's vibrating or whatever, but even at a more fundamental level, it is being shifted by the gravity waves from outer space that are like pulling and pushing the entire fabric of space-time towards and away from the can that I'm trying to grab, okay? Indistinguishable on a human scale, indistinguishable on a planetary scale, as evidenced by the extraordinary endeavor we undertook to either prove or disprove the planet was shrinking or contract or whatever. It was doing this based on gravity, okay? How do we do this? Well, first, we take a sip. Okay? Then we look at the math. And the math says, if you were to build 2 installations on opposite sides of the continent, you could arguably detect a change of space-time, distance, whatever, based on if you could see a tenth of a proton move, right? If there was a single piece of matter on one side of the continent and you knew where it was, sorry, I don't know if you can see this, and you knew where it was, and you had another one that you knew where it was, and if you could measure those 2 things absolutely perfectly, and if you could see a tenth of a proton shift, you could see them move based on the math of how gravity works. So huge gravitational events out in the universe could potentially move 2 atoms a tenth of a proton towards each other or a tenth of a proton away from each other in the largest circumstances, right? In the smallest circumstances, they're moving all the time. But the only thing that we could even ever possibly try and detect is as a tenth of a proton's width. And how on earth are you going to measure if 2 things on the other side of the continent have moved half or less than a tenth of a proton away or towards each other? Great question. Good answer. The Laser Interferometer Gravitational Wave Observatory experiment. Obviously, where we take 2 photons, and I have a picture here, and I'm going to show it to you. So the coherent light source on the left emits a coherent light source, well labeled. That coherent light source is packets of photons, and these photons hit that half silvered mirror, and one of them goes one way and the other one goes 90 degrees the other way. And when they come back and hit the other side of the mirror and travel to the detector, they're supposed to be exactly where they were relative to each other. One goes one way, the other goes the other way, they go the same distance, takes the same amount of time, and bam, they hit the detector at the exact same thing. But what they found is that they were arriving at different intervals. What's that you said? Oh yeah, it could be seismic events. You're right. Because these detectors are 4 kilometers long, any type of earthquake would obviously move the whole rig, or one end of the rig relative to the other end of the rig, by more than a tenth of a proton. Obviously, I could walk up and kick the building and it would move less than a tenth of a proton. But what they had done is they'd isolated all of everything. The tubes are in a vacuum. The mirrors are on a jig that no matter how you push or move, it's like a gyroscopic camera to a proton degree. Okay, so it worked. The photons weren't coming back in the same place. Guess what? You shoot 2 beams of light down 4 kilometers apart from each other and they come back. They're not the same. But what's cool about it is they were able to eliminate all the other garbage that would make them not the same and realize that indeed the planet itself is shrinking or expanding all on its own. And so, you don't know what direction it's coming from. You don't know anything about it. All you know is that one of the arms or one of the legs contracted or expanded. So you build 2. You build 2 of these things. You correlate them through space-time in a way that you know exactly what's happening at each at the exact same time. And when the Livingston Observatory stretches a little bit one way and the LIGO Observatory stretches a little bit the other way, you can correlate the results and detect an emission source. Okay? And not only that, you can take it one step further and you can turn that emission source into an audio signal that the layman can understand. And here is what LIGO detected. Fascinating. LIGO detected that little, okay? But what that was our calculation of this, which is an interference pattern. So as those photons come back to each other, if they perfectly line up, so one is green, one is blue, and the outcome is the red. So if the two line up perfectly opposite, the red line is straight. If they line up perfectly parallel, the red line is, they say, constructively interfering, and it increases the amplitude. So this is how we would detect that half-tenth of a proton shift, is that as the light particles recombine, we can interpret data.
Burning billions of miles away.
But with you, everything scares.
So here's hoping I can explain to you what my question is. What does pulsar timing do other than prove the ocean moves? Great question. As I have explained, I hope you understand, we have known that gravitational waves through space-time affect our existence, affect our, I don't know, lives, our universe. It's a part of our universe, right? So we now know that this and this, I'm creating gravitational waves. Okay, indetectable, undetectable, you'd never, ever, ever be able to detect this gravitational wave that I'm creating by flinging these two masses around each other, but I'm creating it. Can you see it? You can't see it yet? Should I go faster? Oh, no, because you're... Anyway, I'm kidding. I was going to make some stupid space-time joke, but my point is, we've known that this creates something. We haven't been able to detect what that thing is other than, you sitting here detecting it. But at a fundamental level, the gravitational waves that I'm emitting here are propagating through the entire universe. And if you had a detector the size of the universe, you could see me do this. In a way, in if you could see gravity waves, okay? But my point is, based on the infinitely expensive LIGO experiment, we now know that black holes, which are infinitely dense, infinitely small singularities, that when they orbit each other, it creates a significant ripple that our Earth will contract or expand, I don't know, 1/10 of a proton in width. So you can imagine why measuring the lighthouses, and if you go back to the pulsars that I talked about, pulsars aren't new, right? Pulsar, as soon as we started looking up, we saw the stars, and as soon as we started looking at those stars, we saw some blinking, and we saw some blinking in a regular fashion. And no doubt, if something's blinking, you're going to time it, and you're going to time it, and you're going to say, that one blinks that fast, that one blinks that fast, and you're going to put it on a gold plate of society, explaining where we are based on the timings derived from the molecular crap that we put in there, so that you knew what we were talking about, but you could know where we were, at least where we thought we were, in the universe that we are hoping to share, okay? Oh, God. And, yeah, exactly. You're welcome, sharing this universe with you. My universe. Right? I asked you what your universe was. Well, now your universe includes whatever this is, okay? So just sit tight and answer the question. What does pulsar timing do other than prove the ocean moves, right? We knew that gravitational waves existed. We knew that when we sent our spacecraft around the Earth, their clocks ran slower based on their speed, right? We knew this. We've known this forever. So great job, everybody. Way to look at the lighthouses out on the ocean beyond our solar system and say, hey, the timings are different. The ocean's moving. Okay. But there are two different phenomena here. Right? We know that the ocean exists. We know that the space-time gravitational flux exists. We know that we are subject to it. We know that if two black holes orbit each other fast enough, our planet will shrink and expand by 1/10 of a proton, okay? So we know these things. And so what you're saying is, if you look and time these pulsars, you can tell that they're getting a little further apart and they're getting a little closer together. Okay, well, how did we not do this sooner, right? This is the flabbergastion that I'm facing, right? The timings that we receive from the pulsars are in the electromagnetic spectrum, okay? Packets of light, packets of EM, packets of electromagnetism that are making their way towards us, okay? They are interfered and obstructed by, I don't know, the expansion and contraction of space-time, right? The ocean that we look to diagnose, the ocean that we're looking into. So you've got these boats of information that are slowly, or not slowly, they're instantaneously, because it's light. God, speed of light, look it up. C equals MCU. Okay. God. Okay, so is this like a pat yourself on the back type of science experiment? I'm going to drain the taxpayer funds to ensure that on the largest of scales, pulsars, these static beams of light, which we can reliably count on to provide us timing, are ever so slightly changing from each other? It's like, great. Why didn't you look up, why didn't you do this sooner? Right? So now you understand why the scientific community has not answered me, because I see one reply and it says it proves gravity is an ever-present and ever-changing property of space-time rather than be a static void. Well, that is incorrect on so many different levels. You're obviously a doofus. No, it doesn't prove that gravity is ever-present. I've already proved that. You know, your grandpa proved that. Your grandmama proved that. Your whole genealogy evolved in a gravity well, right? How are you trying to tell me that all of a sudden you believe in gravity? Come on, man. What a stupid reply. Waste my space. Anyway, what does, and now we're getting into the weeds of the question, okay? This is where you actually need to think, and I'm sorry it's taken so long, but really, please, bear with me. We know there's a property called a gravitational wave. We know that it distorts space-time in a predictable manner. We know this. We've seen it locally. We've seen it with the precession of Mercury. We've seen it with the supersphere probe thing, that the Planck spacecraft, right? The Planck spacecraft was the most perfect sphere ever made. Look it up. I'm sick of finding tabs. The Planck spacecraft, look that up. Proof, right? And so they're saying, hey, guess what? We've looked at the timings that we've taken from these stars that are so far away, and then we reevaluated it, and it looks like, you're right, guys. The whole universe is full of this gravity wave stuff. No. Sherlock, come on. So, What does it prove other than the ocean moves? Tell me, what does, and again, please understand the basis of this question, right? Electromagnetic emission is a confined packet of energy. It has a wavelength, it has a bunch of other properties, but it's called a photon, okay? And this photon rides on the ocean of space-time, okay? When it enters glass, it travels at a different speed. The speed of light is different in glass, but it is still traveling at max, right? It's still traveling at maximum, right? And so, knowing that space-time is a non-constant, right? It's not a constant. It's not a constant. It's like, of course, those 68 pulsars, their timing is going to change, man. They're moving away from us. They're moving towards us, right? Like, to think that those millisecond pulsars, these rapidly spinning orbital bodies, like it's if you took the entire everything that you think you possibly could know and put it into a ball and spin it at 1,000 or more rotations per minute, right? It's an unbelievable science experiment that's happening out in every single pulsar. But what I'm saying is, if you don't notice a difference in the time that it takes to get here, like, something's wrong with your universe, because in my universe, you can't stand still, right? Everything's moving. If the pulses aren't different every single time, there's a problem or an inspecificity with your experiment. Like, why are you even measuring pulsars if you can't even tell that it's changing, right? No matter how fast you're spinning, you're going to slow down. No matter where you are, you're going to move. And so they're like, hey, guess what, everybody? We've looked at the timings and we've found that, stuff's moving out there. And what I'm basically trying to say is, what is the value? What is the value that you're extracting from this? What does pulsar timing do other than prove space-time moves, man? Like, come on. And again, there's a second part to the question, but what I'm saying is, the boats of light travel on this ocean. And so now that the boats have arrived, what can it tell us about the ocean that they've come from, right? What value is derived from reading the waves of light within the new ocean of gravimetrically distorted space-time, right? They're saying, we've proven that space-time is altered by gravity waves. Okay, we already knew that. So now that all these boats, these packets of light, these photons of information that say, I was emitted from a pulsar really, really, really far away, and now I'm here, and I'm going to tell you that that's where I was, right? And you know that I've ridden this light. I've been stretched out so long that I'm only in the radio wave. And you can look up how a radio wave differs from an X-ray, differs from a visible ray. But what is the value of collecting the detritus upon the ocean of space-time? For is not the measurement moot? Right? Is not the measurement moot? Like, the lighthouses aren't as static as we thought they were, right? Was I really timing myself to the... Anyway. Of what value are the data beheld within the ancestral gravitons whom once perturbed the boats of light at harbor in our port? In other words, what predictions are on offer within this inferred flux of times gone by? And finally, what took so long to measure these pulsars so closely anyway? Were we not aware that timing pulsars was a thing? Or were we unable to time multiples concurrently? Okay? Listen, give me a freaking break, okay? Okay? It was late. It was late. But honestly, take your time with those questions. And I'll be back to explain them, but just, you know what? Just take your time with those questions. Screw it. It's a hard watch anyway, okay? I'll be back. That was more for me than it was for you. All right. Right. It's a lot easier, I'm sure, for you to relate to me than it is for me to relate to you. Right. Look at these exhaustive attempts I've gone through to try and explain a simple, stupid question. Waiting on you there, fella. Right? Waiting on you to explain to me what I meant. And now I hope, after our intercourse, you understand, right? Right? I don't need to explain this any further. Except, what predictions are on offer within this inferred flux of times gone by, right? What I'm saying is, space-time permeates it all, and you could do measuring the gravitational influence on ourselves is valuable, right? But it doesn't offer any preemption. It doesn't tell us what will be. It only tells us what has been, okay? The space-time fluctuations that we're subject to are present, but they are a construct of the past, okay? So we are being influenced by our past. Our universal past, right? Long before you were born, long before but at the same time, right, the atoms within your body are equally ancient as the gravitational waves we're interpreting. And so what value do the boats of light we have at harbor offer towards understanding beyond what is already known? Right? The gateway of gravitational wave, like, what do you want to call it? Gravity, space-time observation, right? Gravitational wave observation is an incredible conduit, okay? But it's the LIGO and LISA experiments. And let's now talk about the future. It's NASA. Why LISA? What is LISA? What is LISA? Okay. LISA, instead of watching a video, is the next version of the ground-based LIGO, okay? This is the space antenna. So what we're going to do is we're going to put some spaceships out in space that are sending lasers at each other. And when those lasers get screwed up when they come back, just like they did here on Earth, we don't have to filter out the semi-trucks and the semi-trailers and the airplanes and the seismic hoopla. We don't even need to create a vacuum because guess what? Space. So we put some mirrors and we put a laser and we put a detector out in space, and we can start measuring local disturbances in our local space-time environment. And we can then extrapolate where those occurrences happened, right? So if we were to put two of, I don't know what the system is, maybe they put 3 mirrors, 4 mirrors, I don't know. But if we're able to accurately and instantaneously measure local distortions in the space-time fabric, then we can slew our conventional photonic collection devices, like the light buckets known as telescopes. We can steer them towards the event that is about to happen, because unlike regular EM radiation, gravitational radiation does not appear to be impeded whatsoever by anything, and will always propagate at the speed of light c in a vacuum, right? So once, let's say, those stars collide, and once that ripple of gravity is flung out, it will permeate the ocean of the universe infinitely fast. And the light emission, right, the fireworks that are emitted are constrained upon that ocean, right? There's no way to ride this wave. You're never going to catch a gravity wave. You can never surf a gravity wave. In my humble opinion, leave it to you to figure out a way to surf a gravity wave. I'm pretty sure you would instantly be traveling faster than possible, right? Like, who knows? Catch a gravity wave, hit up a new dimension. I don't really know. But, and the force-carrying particle, which makes up this ocean, right? How could, right? So it really is the fabric, right? And so what I'm saying is, these boats on this fabric, these boats on this ocean, what value are these photonic boats that bring us these tales of far off places, right? And you're suggesting that it can only tell us about the ocean? Well, hey, let me tell you, sailor, happy to be ashore, but my trip took me 0.3 seconds longer than it should have. Okay, great. And the only reason to know that is because we're looking at the boat. But if this LISA experiment is successful, we'll be able to see the wave that emitted the boat. And so the wave crashes ashore, and then we can say there's salvage out yonder, right? So, and this has been done before. There are a number of, like Swift. Look at the Swift spacecraft. Hold on. God, people. Okay, so here's our attempt to find the first boat that comes from a cataclysm, okay? So NASA's Swift is intended to detect gamma ray bursts. Okay. Every boat on the ocean travels at a different speed, okay? The higher energies have a lower wavelength and a faster propagation time, but are easily interfered with, okay? So the radio waves, those long suckers that are meters long, versus these gamma rays, which are micrometers long, you can imagine, right? What is me talking like this? The other is me talking like this, right? So they propagate at different wavelengths, and those different wavelengths interfere with the other manifestations upon the ocean of space-time, which we all are drowning in, okay? So gamma rays get here first. They're the fast ones. Those are the cigarette boats from Cuba with. So they get here first. And then we slew the scopes. We say we got gamma ray detections. Get the X-ray scopes over there first. Don't even talk to me about capturing X-rays. I don't even know how they capture gamma rays, right? X-rays, like we all understand how a telescope, because we've all seen a mirror. But have you ever seen an X-ray mirror? Right? And so look up challenge question. How do you focus X-rays? Right? And once you understand that gamma rays, X-rays, light waves, visible light waves, all that crapo sails on this ocean, right? So when this Swift observatory came online, the idea was we can grab these gamma rays and then get our regular light buckets to scoop up the rest. And so this was an advanced warning system. And so the LISA, the laser interferometer space array, would be an advanced detector for events to come, right? Like you would see this gravitational wave disturbance, and then you would slew your Swift observatory and your other ones towards what would become, right? So you get this wave, you're like, hey, there's a tide coming in and there's going to be a bunch of boats on that tide. Get your, I don't know, boat trappers? I don't know, whatever. You get your telescopes ready to see the boats. And then this hoopla around affirming that the ocean roils, it's a roiling ocean, right? What value is knowing that the ocean roils? Who cares, man? Right? And why did it take so long to confirm this, right? These pulsars were pulsing at these super precise intervals, and you're only now telling me that the timing has changed? Dude, gotta set my clock, man. The right question. Gotta set it to the right question. That's okay. I'm used to being ignored. Oh, wait, no, guy. No. I'm ignoring you.